Hello everybody, my name is Walter Bauer and we're here in the NMR room of the Institute of Organic Chemistry of the University of Erlangen in Germany. And behind me you see the magnet of our Geo 500 megahertz, and on bottom, at least in part, you can see a solid state NMR magic angle spinning probehead. Not very exciting, to be honest. But I'm going to talk about a phenomenon which is long known and which is called eddy currents. In German, Wirbelströme. Before I continue, I should mention and I should apologize for the noise in this room. You can imagine all these devices, they contain many fans, and so it's a little loud. Hope you can understand. That's, by the way, the reason why I have the microphone here and do a separate recording of the sound. Anyway, eddy currents are used, for example, for eddy current brakes in trains. So they are of benefit. But eddy currents can also be a problem, and actually a phenomenon which I didn't know until a couple of weeks ago was the influence of eddy currents on magic angle spinning. And actually these eddy currents can be a problem and can even spoil the quality of a magic angle spinning measurement. Before we continue with the experiments, I'm going to give you a brief introduction about the phenomenon eddy currents, what are the physics behind it, and after that we go into the experiments carried out here in the NMR.
As a magnet falls, it's creating a current in the copper pipe. The electrons in the copper are moving.
Those induced currents are called eddy currents because they circulate like eddies in water.
As they move, they are also creating a magnetic field around them. Lenz's law states that the magnetic field created will oppose the original magnetic field. These two fields oppose each other, and so the magnet, being repelled, will fall in slow motion.
The shiny metal disc in the electric power company meter outside your house rotates as a result of eddy currents. Eddy currents are induced in the disc by magnetic fields caused by sinusoidally varying currents in the coil. The metal detectors used at airport security checkpoints operate by detecting eddy currents induced in metallic objects. The metal detector at an airport security checkpoint generates an alternating magnetic field. This magnetic field induces eddy currents in any conducting metal objects carried through the detector. These eddy currents in turn produce an alternating magnetic field. This current induces a current in the receiver coil, which in turn produces a beep.
This short video shows how our eddy current brake functions. But at first I'm going to describe my setup, which is shown here. The collets hold a magnet, which was harvested from a dismantled hard disk drive. The chuck from the Mills motor holds a copper disc with a diameter about 60 mm. The cross staple is used to move the magnet over the rotating disc without letting the magnet touch the disc. This will lead to deceleration of the rotating disc and transforming rotational energy into heat. Now we'll show how quick the disc heats up by bringing solder in contact with the disc and melting it.
So I'm going to demonstrate now the difference between a non-conducting material and graphite, which is conducting the electric current. First of all, I have this meter here, and if I shorten the two pins, you will see the deflection. We have now a resistance of 0 ohms. Once again, shortening, 0 ohms. Okay, I take now the non-conducting material. It is an organic acid, to be precise, diphenyl acetic acid, a white powder. And now I tip in the two pins and watch the meter. What happens? Nothing. This material is not conducting the electric current. Alright, let's take a different paper. And now I pour the graphite on the paper. When I now tip in with two pins, note the meter, what will happen? Actually, graphite is conducting the electric current. We have now a resistance roughly between 500 ohms and 1 kilo ohm. So graphite is not as good in its conducting abilities as, for example, iron or even gold. But actually, you see, graphite is a conductor for the electric current. Well, what you can see here is a magic angle spinning rotor and this very tiny turbine, which will sit on top afterwards, and a small funnel. I'm inserting the rotor into the funnel, and I'm taking now diphenyl acetic acid that we've seen before, and which is, as you know, a non-conducting material. Fill it into the rotor. Take this plunger to make it a little more condensed, more tight. Repeat this a couple of times until eventually the rotor is filled. Okay, looks good. Let's repeat the process. Okay. Now you can see the filled rotor. I'm pouring it out. Here we go. See the black powder inside. Now the rotor is capped. The turbine. And the turbine is screwed, so it gets tight contact with the rotor. It's tight now. Do some cleaning. And now we will be inserting the rotor into the magic angle probe head. Okay, I'm sitting here in front of the magic angle spinning probe head, and here we have the hole where the rotor is filled in and will spin in the magic angle of 54.7 degrees with respect to the direction of the magnetic field. The rotor filled with diphenyl acetic acid. I'm going to insert the rotor and start driving it. And we'll be hearing, hopefully, the rotor starts to spin. We have 2.4 kilohertz at the moment. And now in the second stage, the air is increased and the speed increases up to 5.1 kilohertz. Hope you can hear the sound. I'm lowering the cap now, and I'm going to insert the probe head into the magnet. And you will note there's no difference in the frequency regardless whether the probe head is inside or outside the magnet. We still have 5.1 kilohertz as the spinning speed. So let's continue. I take now the very same rotor as before when it was filled with the diphenyl acetic acid, the non-conducting material. Insert it here. And now I fill in the graphite that we've seen before. Eventually put some pressure on it to make it more dense. Now we want to cap the rotor. You can see it. Okay, and we screw it. And now everything is tight, as you can see. And now we can take the rotor and put it into the magic angle spinning probe head. Okay, I'm taking now the rotor, which is filled with graphite, and I'm going to insert it into the MAS probe head. I leave the cap on top just to make you see that the rotor will start to spin. And I'm switching on the rotor air. The rotor starts. You can hear the sound. We have now roughly 2.4, 2.5 kilohertz. And now in the second stage, the speed is raised, and we have now 5.2 kilohertz. You can hear the high tone, which is sometimes quite annoying and may lead to deafness, actually. And I'm lowering the cap. We have still 5.2 kilohertz. And now I'm going to lift the probe head into the magnet. And now listen to the tone. You will note the tone will decrease the further the probe head will stick inside the magnet, inside the center of the magnet coil. Okay, here we go. You can hear the sound. The frequency decreases, and as I get further and further into the magnet, the rotor eventually will stop. So this is a quite good demonstration, I think, of the eddy current effect, which takes place in a moving conductor inside a magnetic field. Now I'm lowering the probe head, and you hear and you see on the display that the frequency is raised up again to the old value of roughly 5.4 kilohertz.